Good afternoon. I'm going to talk to you about thermosets. So there's some three systems that we offer, those being PolyJet, stereolithography, and also the DLP systems. We're going to go through an overview of the machines, what they can do, some very top-level applications that they can do as well. So we have 5 polymer systems, of which the PolyJet, stereolithography, and the P3 are looking at these thermosets where they're cured with UV light and it's a photopolymer. There are different use cases specifically for PolyJet, along with stereolithography, and also with the DLP system, the P3. So I'll start off with PolyJet. So we have a range of machines that offer you different capabilities. So whether you're wanting to do fully rigid parts or opaque parts, if you want to wrap them with different graphics or bump map surfaces, whether you want them just monotone as well. So we have different systems, so the J8 series, the J35, the J55. We also have systems for the medical sector and also systems for the dental specifically, which I won't touch on today. Two clicks. The first one, creativity for your RP shop. So we have the J850 and the J35. So you can do these very quick concept models, high speed. So we have the Vero draft grey and the draft grey mode, so you can do it very, very quickly. Has a big build envelope, gives you really, really good detail, high accuracy, lots of materials, and obviously the integration with the GrabCAD software as well gives you that extra design freedom on the machines themselves. Even though this is quite a large system and relatively expensive when you look at the size of the machines, we do have a smaller system that has the same capabilities, just a different build envelopes. So really, PolyJet and the Stratasys J8 series is the only solution that provides the end-to-end throughput from the design process all the way through to the prototyping, functional designs, and also some end-use tooling as well as. So the operator of the machine can run different materials, can preload different trays onto the machine, all queued up within the software. As long as you have the right materials loaded into the machine, you can just hit play and run the next one. So if the J850 is too big for your workshop, or the build envelope's too large and you don't need that size, there is the J826 again. PolyJet allows you to do full colour, Pantone certified materials, as well as there's different colour codes that you can use inside as well to give you the surface finish, the details and the colour accuracy that we want at a lower cost. Same quality as you would get from the J850. We also have the J35 and the J55, so they're slightly different technologies. So PolyJet is basically like a glorified inkjet printer. So we have the head and we deposit material droplets, but instead of obviously ink, we have the photopolymers. This is those systems are filament lamps. The J35 and the J55 are LED light sources, so it's more sustainable. But the build process as well is different. So the J8 series, they use a Cartesian system where the head moves left to right, it comes forward, moves left to right again whilst depositing material and curing it. I'm full with this slide, sorry. Whereas the J35 and 55 has a spinning build platform and the head just moves back in one position. Different types of materials because the wavelength's different with the LED light source. Different print volumes as well, very good for office-friendly use, and we also have the Pro Air system to take out those smells. J35 is basically a monotone system, so you're only doing blacks, greys, whites, along with some flexible materials, whereas the J55 gives you the option for full colours as well as. When you compare the systems, you've got the 35 Pro, the 55, the J826, and then the J835 and 850. There's different build volumes that you can do and different materials as well. So if you look at the J35, say it's monotone, you can do transparent materials, you can do the draft grey, you can do flexible materials as well, and also a digital ABS material, which has higher HDT, better mechanical properties than the normal Vero materials. The J55 Prime gives you the full colours, the Pantone certification, but doesn't have some of the other materials like the flexible materials and the digital ABS. You have to move up to the J826, which gives you those additional materials, and obviously the flagship systems, the J850, with all the materials as well, and a much larger material cabinet, so you can have a longer unattended running time on the machines. So typically the J35 and the J55 are used for these concept verifications, so you have really nice surface detail, high throughput, Also low cost per part with the Vero Draft Grey. As you can see the examples there on the screen about going from just the plain single colour, adding more detail, adding graphics and logos and printing it all simultaneously on the machine. Also with the J55, so moving on from the 35, you can then introduce the different transparencies, the colours, and take the designs to the next level for your prototypes or functional prototype designs. You can combine different materials, so you can do overmolding with the elastomeric-based materials. Obviously, do different colours on there as well. So there's examples on there for shock absorption. So with elastomeric materials, you can vary the short hardness of those materials to meet the needs of whatever the application is that you're looking at doing. Applying the graphics and the textures around gives you that full realism to be able to hand it out to your customers, to give them that interface before you go down the line of the traditional methods of machining or tooling and making prototypes in a different way. I mentioned about applying graphics. So with different softwares, you can apply VRMLs around the outside. So again, this is all printed in one go. It's color reference with the Pantone certification, good detail, 14 microns resolution on there. So you're really getting that if you're trying to put your brand onto a part, you can print it all in one go and get it off the machine. So it's a really, really nice way of doing those new packaging examples here, but it could be absolutely anything. And when I say anything, it can literally be anything. So these are eyeballs printed on the J8 series, and they are actually end use and they can go into people's sockets, which is not pleasant, but you can do it. The realism is sensational. If you look at that, you wouldn't know that that was a 3D printed eyeball. It does require some polishing, so it doesn't come off the machine looking as polished and shiny as that. So there are the post-processings that you have to apply afterwards to get that surface finish, and maybe a light coating over the top to give you that nice gloss finish on the machine. So when you combine the design cycle, so again you've got the concept models, the draft grey, adding more details into, you've got the leather stitching around the outside, then applying colours, and then applying more graphics or wood grain textures over the surface of the model. So again, it's polished afterwards, but it's a really good example of what you can achieve with PolyJet. Now the elastomeric materials, again in full colour, so it gives you the ability to print some pretty amazing parts. So the chap on the left, it looks so realistic, it's unbelievable, and you can pen the ears back and forward. But again, done on all the PolyJet systems as well. So there's amazing qualities that you can get. Stratasys, we also have the option, there's a research package machine, so you can put different materials in, you can print on different substrates like glass, wood, or fabric. And because of the textiles or the fashion industry wanting to adopt 3D printing, we actually created our very own machine for the textiles or the fashion section, so you can print parts directly onto fashion, onto different types of fabric. They can actually be washed in a washing machine as well. So I think it's something like 500 to 600 wash cycles, 30 degrees C. Also have all the UV resistance data that goes along with it. So again, very, very amazing applications, printing on leather handbags, all sorts of things as well. Fashion, textiles, things like that as well. So as a sort of an overview of PolyJet, the use cases are very wide. So it's not just fashion, it's not just something that looks pretty, but you can do injection mold tools for very short runs. So if you only wanted sort of 10 or 20 parts from a tool, you could validate that design, print that tool, do a short run on a part, and then you can go down the traditional route of manufacturing the actual injection mold tool. You can do some jigs and fixtures as well, but there are significant differences between the material and mechanical properties on PolyJet as there is to DLP or stereophotography or even FDM. So they're not sort of like engineering grade plastics that you're printing. So a little bit more brittle in comparison to other materials that you may be used to. The next technology is P3, which is a DLP technology, so digital light processing. It was recently acquired by Stratasys, and it's a totally different technology to what we have as our core, which was the PolyJet and also the FDM. So DLP, you have a projector, so it's a bottom-up approach. You have a projector underneath a tray of resin, you expose the light and it cures and solidifies and moves up layer by layer. The difference here between PolyJet or stereophotography is Whether you print one part or 20 parts on the same platform, it takes the exact same amount of time to cure that layer, because you don't have the scan speeds or the tool paths with the FDM extruding it out across there. Also, because of the wavelength of light, you're able to do some amazing plastics, much better than PolyJet or even Stratasys. So you can get some really high-grade, high-impact modified nylon 6/6 materials, or materials that are filled with higher HDTs. Different flexible materials as well, with different shore hardnesses. There's medical grade materials as well, so biocompatibility for skin contact, mucous membrane, so for hearing aids. There's also a range of additional materials for the dental market, so whether that's just for the crowns, copings, fitments, those sorts of parts, or castable resins as well, that you can print on this machine. Relatively small build envelope in comparison to what we have for a lot of our machines, at 192mm by 108 by 370mm in the Z. And it's also, we have multiple materials already certified. It's an open source material system as well, so you can try different materials in there if you want to, with the open material license with it. But it's totally different when you come to processing parts and the methodology about thinking how to print parts compared to PolyJet and FDM, which is where you just put them on the build tray. It'll create the supports for you, you can wash them off or peel them off afterwards. With DLP, you need to look at the orientation. The taller the part, the longer it's going to take to build. The lower the part, the quicker. Angles and orientations depend where you're going to put the support structures. Support structures are going to affect the A face or the B face of a given model. So really, you need to pay attention to the way you do this. Design for additive manufacturing as well makes a big bonus, because if you can add chamfers or filleted corners onto designs, you can remove the need to have as many supports on there. One of the key advantages of the DLP, the P3 system, is that we can do greater overhangs. So typically most materials will do 3mm from a 90-degree overhang without the need for supports. Some can go even much longer, sort of like 10 to 15mm span distance from 290 degrees. So again, you're reducing the amount of supports needed on the system and that on the parts, because that's all to do with the separation mechanism we have. The peeling forces are greatly reduced, and it's also down to the software that we have in the machine or monitoring the machine to see what's actually happening. You can do very fine details, very thin wall structures, and obviously there comes a point where there's no point in going too thin because the materials will just snap anyway, so you have to think about those design constraints when you're designing the part itself. The machine, it's just a projector that flashes a light on and off and it cures resin. There's a lot of software in the background that maintains the system, so we're looking at separation forces, we're looking at the exothermic reaction of the material when we expose the light source. Very much like FDM, it's an enclosed system with a door and a seal, so we're maintaining the temperature inside, which allows us to use some materials that most people can't do. So for example, like the 3955 material as well, allows you to do high heat temperatures, but because we have those tight controls thermally on the machine, we can build from the full Z height on the machine as well. There's a plethora of different sensors inside the machine, monitoring the humidity, as well as the motion and the atmosphere inside, so that it's more of a manufacturing production machine as opposed to an LP. You've got traceability, you can pull reports from the machine to see what's happening during the build process. If there was a quality control issue, you could backtrack it and give you some sort of conformity to go with it. Materials, there are loads. So 3955 I touched on, has a HTT of around 280 degrees C. And that's looking at replacing all 10 orphanolics, materials like that. These are not materials that Stratasys has made. They're partnered with Loctite, BASF, Covestro, and other systems as well. If you don't need a high temperature like 280 degrees C, there's one around 120 degrees C. Depends on the ultimate tensile strength and the elongation of break, but typically there's a material that will fit most needs if you're replacing downloading things as well. There's elastomeric-based materials, as I've said, anywhere from around sort of 45 Shore A to around 80, depending on which material you're going for. Slightly trickier to build with, again, so your design considerations are different. Also slower to print just because of the viscosity of those resins. Some examples that have already been done. So there was a competition in the US where they wanted to redesign and look at AM to print bracketry for the F-16 Fighting Falcon. They used the 3955 because of the FST compliance that it has, and also the chemical resistance to hydrocarbons and aviation fuels as well. Because this material has been around for quite a while, there's also additional data available on thermal stability, UV resistance of those materials as well. So this did freeze testing and also flammability tests, and it passed the tests. So they were able to actually print the parts and fit them to the fast jets. Sticking with the 3955 material, so this is fly-by-light as opposed to fly-by-wire. So for those sensitive fibre optics or cables that you're going to run through vehicles or aircraft, it makes perfect sense to use this material as end-use components, so T connectivity. Use these systems as end-use parts printed and then ship them out the door and fit for purpose. Obviously, you can customise and put labels on as you can do with any AM process. There's other materials, so 3843, which is also a 996 based material. Good impact resistance, but very nice to be able to drill it and tap it and put inserts in as well. Really nice surface finish that you get off the model, so that you don't have to do any polishing or sanding apart from removing those witness marks where the supports are as well. So where FDM isn't suitable because of the surface quality, or PolyJet isn't suitable because of the mechanical properties of the materials, P3 fits in really nicely in between those sort of sectors as well. It's very quick to print, again, so 2.5 hours for the two parts at 80mm high at 100 micron slice heights. You can change the slice heights. Currently, most of the parts we printed are 100 microns because the surface quality is so good, but there will be different slice heights coming out in the future. Connectors for automotive, aerospace, and medical, it's a massive area, and because of the accuracy, the surface detail that you can get, connectors is one of the key markets that have been one of the early adopters for DLP with the P3 machines. Fit, form, function is amazing. Mechanical properties with snap fits, it just feels like the injection molded part. It's cheaper, obviously, it's quicker to do as it would be with AM, but it's also much quicker to print on the machines. You don't have to do one layer, you can stack them as well, and do builds overnight or over the weekend for sort of unattended use. There's a tray, if you go and have a look at the machine inside, it can hold up to 2 kilos of resin, so you don't have to keep on going back and filling up that machine. Low volume, obviously, we can't do hundreds and thousands of parts on this system, but if you wanted to do, for example, 30 to 40,000 very small connectors a year, it's very easily achievable. Larger ones, maybe 10 to 15,000 connectors a year. Because of the elastomeric materials, you can try out some rubber seals and gaskets as well. And there's also been examples of printing extrusion dies where you can extrude tens of meters worth of the actual elastomeric material you want to use. Again, it's cheaper than going out and investing in the actual tooling if you're just going to try out something where you have that low volume production that you need to do. So that's a brief overview on the DLP. Really versatile machine, good range of materials, and lots of use cases across the different sectors as well as. Then we come on to the Neo range. So Stratasys, as Andy said earlier, we sort of widened our portfolio and we purchased a company called RPS. RPS was a group of guys that used to work heavily with 3D systems, used to service and install machines, and knew all of the issues and the teething problems that you had with those, and they basically created a machine that was more user-friendly, also open source with the 355 nanometer wavelength materials, but some really, really interesting changes with the Zephyr blade, the way it recoats the material inside, the way we have the controls on the laser, and also the material leveling sensor as well. So you get more consistency, more accuracy from the machine. There's two machines in that range. There's the Neo 800, and as the name says, it's 800 by 800 mil by 600 mil in the Z, and it's a 2-watt variable beam laser in there. So we're never going to use the full 2 watts of power from the laser, so the longevity of the laser, it's going to last you for years on the machine. You can change the beam width, so for the outside surfaces of the mold, you want it nice and detailed. Good surface quality, you can change the beam width from where you want much sort of the infill patterns. You go for a wider beam, so it's quicker to print on there as well. So you get really high quality parts, low variability rates, so there's not as many failures or issues or surface defects that you would get from many of the other systems out there. And clearly it's a very highly repeatable system and highly reliable system as well. Layer thickness is anywhere from 100 microns down to 25 microns, and you can go even thicker. It depends on the materials as well. This system, by the way, when I show you the next one, the smaller brother, the 450, the 800 is about 40% quicker over the Neo 450 series. This has a build envelope 450 by 450 by 400, so it's smaller. Again, it's still open source. You're still getting high quality parts. There's an E and an S mode, so you have the standard mode and also a different one with a 2-watt laser. The E is the one with the 1-watt laser, and the S with the 2-watt laser. Beam size has changed depending on the machine, so the standard one's 80 microns to 750 micron beam width, whereas the lower spec one's 250 micron beam. So you're not going to get the same surface detail as you would do from the 800 or the S model. Loads of different applications. Most of them are to do with tooling or wind tunnel testing on there as well. So there's an example from McLaren using the Perform Reflect material, 30% less post-processing time as you would get from the normal white performance. You don't have to paint the part afterwards. Excellent surface detail and resolution. So thankfully McLaren have purchased multiple machines from us and seen a massive reduction in post-processing times by up to 80%. It's not just wind tunnel testing, so FDM is used for concept tooling, and again that's in aerospace, defence, automotive, but with FDM you have to do a lot of post-processing to get back to the right RA value for those tools. With the SLA, you don't have to do as much post-processing on there, so you're going to get really good surface quality from it when you vacuum bag it and put it in as well as. One of the massive cases that I think tends to get overlooked in stereolithography, obviously it's prototyping, it's concept modelling and things, it's also casting. So the examples that you can do of large castable parts very cheaply as well, because they're hollowed out with tetrashell from materialised magic. So you can do a large turbine, sort of 800 mil by 800 mil. It's only going to cost you maybe sort of 200 300 pounds to actually produce that model, and you can go down the traditional route of casting. There are loads of cases out there, and again, I don't have time to go through all of them. Am I good? Okay. So Paragon, as an example, is a service bureau, again, for dash consoles and vehicles, or those concept designs or prototypes for a new vehicle or whatever it may be. Again, stereolithography makes sense because of the surface quality, the time to print, the reduction in costs associated with time, and also the material consumption. So typically, you would machine it back, 2 to 3 days. You can print something overnight with the Neo system. Different use cases, so this is a different material, so Sonos evolved the 182. So they were building a car, they needed to get some parts to fit in it to do some functional testing, as well as the fit, form, and function within inside the vehicle. They didn't have the time to wait to do the traditional route, so it's much quicker and cheaper to do it the AM route, but they still had the ability, because of the material properties, to do some functional testing with it. And then when they actually got the part they were meant to get, they were able to swap it out. So significant cost reductions and also lead times. And I've just realised I should have put a lot more slides in the deck because I have finished. So thank you. If you have any questions, feel free to ask.
Any questions, guys, for Matt? Just a round of applause, I guess.